Planck told you that if I take my light as light's energy as a quanta, small, 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 nh nu, then the black body radiation was explained. But the key question was why I should take this. That was the key question. If I assume this, then black body radiation explained. So then came the genius of Einstein, who told you something else, something different, and who altogether rejected the classical theory of light. But as we know, we still have both the classical and quantum theory of light, and after 20 to 30 years there were another theory which combined this classical and quantum and all, and proper quantum theory of light. That's a long story about that, we'll discuss later. So okay, we now go to discussing the photoelectric effect and Einstein's postulate about it. So I remove myself from the screen. So photoelectric effect was a phenomenon which, by brief, I tell you, light incident on a surface of metal, semiconductor, whatever, initially we tell you metal, electron emitted. So a brief schematic diagram should be like this. It's very big. Okay, light coming on to a surface of some metal, and it's emitting electrons, and the whole thing are inside in a closed tube, and the electrons potential, how much electrons is emitted and what is the energy of the electrons, all this will be measured by this circuit, which is nothing but resistance and voltage. So if I do maintain an opposite voltage, so that actually repels the electron and it can even stop the electrons. I'll tell you this and stopping potential. So okay, first thing first, light comes, strike a surface of metal, and electrons come out of the metal. Three important phenomena was observed: that emission of electron is very quick. It takes 10 to the power minus 6 seconds, that means order of microsecond, to emit an electron. What is the big deal with it? I'll discuss, of course. The classical theory of light, actually, the wave theory of light, cannot explain this. According to classical wave theory, energy divided in wave forms, and that waveforms comes together, comes one by one, one by one, one by one. should take some finite time, order of, not order of microsecond, order of seconds and minutes, second and minutes to emit an electron. So that very strange phenomenon of very quick response, that quick response of electrons was not clear from the classical theory of light. Some more interesting phenomenon is the electrons actually, depending on the emission of electron, depending on the wavelength. Suppose you are giving red light to some metal, so you can see that there are no electrons emitted. If you see if you give a green light whose wavelengths are smaller, then you might see, you'll see for this particular metal, you'll see that there is some electrons whose maximum velocity is around this. So this is 550 nanometer of light with energy 2.25 electron volt. This is 700 nanometer of light with energy 1.77 electron volt. Finally, if you apply a violet light, you see that the wavelength of violet is around 400 nanometer. It have 3.1 eV of energy, and that emits an electron with energy 6.22 into 10 to the power 5 meter per second. So the main observation was emission maximum energy, and that is actually the stopping potential or maximum velocity of electrons measured by that stopping potential depends on the frequency of light. It is same as wavelength. Frequency and wavelength are the different things. It's depending on frequency, that means depending on the wavelength. The frequency of incident light. And not on the intensity of the light. That is also a strange phenomenon according to the classical theory of light. Classical theory of light, energy of light is proportional to the electric field. That means energy will be proportional to the intensity. Classical theory tells me classical theory of light tells me that energy of light should be proportional to its intensity. It's almost equivalent to its intensity. But here it seems that energy, maximum energy of the electron, which is of course coming from the that energy of electron is coming from that incident light, is depending on somehow its wavelength, not on intensity. So if you give if you give different intensity, but if a dim light or higher brighter light, but with same frequency, that maximum velocity of electron becomes the same. So maximum velocity of electron emitted depends on frequency of light, not on the intensity of light. That is not that does not go well with the classical theory of light, which predicts that energy of light should be same as its intensity. So depending on intensity, that maximum velocity of electron should have depended on. So that is a problem. The third thing is, then what the intensity is acting for, what the intensity are doing in this photoelectric effect, that intensity actually increasing or decreasing the number of photoelectrons. That how many electrons are emitted. Higher intensity of light incident, that actually increases the photocurrent. But that should not have been there. From the classical theory of light, higher intensity should increase the velocity of the electrons more. Of course, higher intensity will increase the photocurrent. That is not an issue. But it is only increasing the photocurrent, does not affecting the velocity of electron. So these were the observations. If you want, I can give you some another 1-2 data there, but main part is the corresponding physics. So that brief discussion of our brief discussion of the experimental photoelectrons. Now I will focus more on what Einstein, how the Einstein explained it. Einstein explained in this way that he altogether, what Einstein did, he actually given a dramatic proposal that he told you light is composed of photons. What the hell the photon is? Composed of photon. Photon acts like a particle. Photon like particle. The photon comes, attacks something, collides, collisions. So that is a dramatic change from the classical theory of light. So he told you, okay, light is not a wave, but why should light shows the property of wave? Then it comes some another part of the story, which we'll deal later. But what Einstein proposed it, and thus Einstein actually given the birth of quantum mechanics itself also, that light is composed of photon. That energy quanta, each photon have energy h nu. How come this nu comes? If it's a purely a particle, that nu should not be there, but it acts like a photon. It's energy quanta. So at that time, photon energy quanta have frequency. Energy of quanta is h nu. Momentum, it acts like a particle, so it's do a collisions. So its momentum p should be h nu by c. That comes from the story of relativity, that massless particle energy is pc, and p is energy is pc for massless particle. Photon is a massless particle. So photon acts like a particle, zero mass, and follows this relation. If we have n photon, it have n h nu, but a single photon have h nu of energy, and it have a frequency which can be measured by directly as light have a frequency. So light, if observed phenomenon, we cannot reject. So it have a frequency, but it's very smaller level. In very small level, it acts like energy quanta. It acts like particles. Okay. So we'll discuss the Compton effect, where the particle nature of light will again be measured properly, will again be manifested properly. So then if I assume that light have energy h nu in energy quanta, so then we explain like this, that if you have a metal surface, when lights are coming, actually the small photons are coming. So light collision, light falling on a metal surface, classically it was viewed like, okay, some waves are coming, a continuous flow of energy, blah 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 blah, and its slow absorption into the surface, and that theory is rejected. It's like a kind of a quantum phenomena begin, that light falling on a metal surface is actually viewed at a flow of energy quanta, or flow of photons, like particle colliding. Ions hitting the surface and kicking electrons out. धाय, एक लात मार, धाय, kicking the electrons out from its domain, from its den, from where it was in the metallic surface. Okay. So then what he proposed, then there is a work function there, of course. Each metal have their own barrier, of course. A metal have a different surface structure, their own surface structure. Some potential barrier would be there. Of course, electrons are not very free. Electrons were, of course, a free electron, but of course they have some barrier in their potential barrier kind of thing in the surface, so that electrons are not moving out automatically. So some potential barrier on its surface. So that part I called you phi. So photons should have a minimum energy to start kicking out of the electron, the electrons, and that minimum energy is called work function, called phi, and that depends, of course, on the material. You know that not always metals are used in a solar panel. What is used? A semiconductor. Depend on the material. So then when the photons have higher energy than the phi, then that extra energy than phi is converted, extra energy than phi of the photons is converted into kinetic energy of the electron emitted. And that I forgot to mention you. So that kicking out of the electron like colliding photons actually solves the first problem. Solve that quick phenomena, because if we treat photons as light as particles, so as photon acting as a particle, so that elastic collision with the electrons in the metal is very fast. So that solves the problem of quick process, that it takes very small time to electron coming out from the surface. So okay, I should draw this a little bit below. So finally all these things resulted in equation, that is half of m v max, maximum velocity of an electron, is h nu minus phi. Of course, phi is the work function, h nu is the energy of a photon, and it's the maximum energy of an electron. So we are dealing 1 to 1. That's one electron, one photon energy. One photon have h nu energy, one electron have mv square, maximum velocity, that is kinetic energy Ke of electron, energy of photon minus potential barrier of the surface. That looks more physical. So you don't remember like equations, you remember the phenomena, you remember the what happens there. Equations will of course come out. The potential barrier of the surface. We all have read something, some form that photoelectric effect in our class 11 and 12, class 12 to be precise. So in this course we don't need to go much beyond this, in not very much more detail of photoelectric effect. So what conclusion we draw? Planck initially told you that light energy quantized. Then Einstein told you, of course, light composed of particle like photons. With energy h nu, momentum h nu by c. And then we'll study Compton effect. Here it proves it's another phenomenon of this, another phenomenon like photoelectric effect, which proves this to be true. Compton says, of course, photons do collide. Photons do collide like particles. So we'll study Compton effect in the next class. Okay. Bye-bye.